Assalamu alaikum. This is lecture 4 of Information and Communication Technologies, and in this lecture, I'm going to discuss some concepts about memory devices and processing devices. So here are the lecture contents. I will briefly revisit the machine cycle which we discussed in the lecture 1. Then we will move our discussion to memory devices, and most commonly used memory device is the random access memory. Then on top of that we will discuss other memory devices which are used by the processors. These memory devices are registers and cache memory. Then we will move our discussion to the processing of the system, and to maintain the processing we have to have a system clock in every CPU or system level clock. Finally, we will conclude our discussion with the description of some CPU architectures which have been used in the past and are currently used in a different variants of processors. So if you revisit the machine cycle, you can recall that machine instruction cycles involved few steps which consists of fetching the instruction from the memory and then execution of those instructions in the CPU and then storing the results back to the memory. So machine cycle is the steps by the CPU to process the data. Machine cycle has two subcycles, the instruction cycle and the execution cycle. In the instruction cycle, CPU fetches the instruction from the memory and decodes the instruction. In the execution cycle, CPU performs that decoded instruction and stores the result. Sometimes it is required, sometimes it is unessential. So usually these instructions happen at a really rapid pace in and measured in millions instructions per second and even billions of cycles or billions of instructions per second. So if you look at the example, we have the execution cycle, the instruction cycle and the execution cycle here. In the instruction cycle, the CPU sets the instruction to fetch the sound, which in the steps is referred as play sound, is sent from the RAM to the CPU. That means CPU fetches the instructions or the data from the RAM. The control unit breaks the command into the instruction and sets the CPU that can handle. In the execution, the command or the control unit executes the instruction and the command is sent over the system bus to the sound card, which announces the sound of the music. So most of the current processors involve pipelining whenever using the machine cycle. So pipelining helps to increase the CPU processing, as with each step you can perform the instruction and then fetch the next instruction. So in the pipelining, processor begins the fetching a second instruction before it completes the machine cycle for the first instruction. So as you can see, in the machine cycle without the pipelining, you have fetch, decode, execute, store cycle, and in the four steps you can execute only one instruction. However, in the same four steps you can initiate four instructions, such as in the first step you will fetch the first instruction, and in the second step you will fetch the second instruction, and the first instruction decoded. In the third step, the first instruction moves to the execute and the second moves to the decode phase, and CPU is free to fetch the third instruction. In the final phase or the final fourth step, the CPU stores the result of the first instruction, executes the third one, decodes the second one, and fetches the fourth instruction. So all of the information in the machine instruction or the machine execution cycle is carried from the memory to the CPU. So in the von Neumann architecture, we have a concept of stored program. That means the program is stored first in the memory and then it is moved to the CPU. So if you draw a conceptual diagram, we may have the CPU in the center and we may provide it some input and it can provide us with the output, and memory is directly linked with the CPU. So this is the concept of the von Neumann architecture. So this concept or this architecture helps us to understand the information that the program is first loaded into the memory and then it is accessible to the CPU. So it stores all of the instruction that is needed by the program and all of the data which is associated with that program. So more memory usually makes the computer faster because it helps to cater more programs in the memory at the same time so that the CPU may have access to those programs and execute at a faster rate. So the memory stores instructions waiting to be executed by the processor. So data is also needed by those instructions which is also part of the memory, and the final results are also stored into the memory. So as you can closely look at these arrows, it shows that it is a two-way transmission. For example, once you provide the input or if you read input from some storage device, this input is transferred to the memory and then CPU reads the instruction from those memory to perform some operation and it outputs the result back to the memory which was propagated to an output device. So the memory usually contains three basic categories of items. It can hold the operating system and other system software, can hold the application program, and it will hold the data that is associated with the program or process with the resulting information. So whenever you access the memory, you are referring to the location in the memory unit. So to access the memory, you must have the access to the location of the data into the memory slots. And the smallest possible memory slot is the bit in the computer memory. So bit is the smallest storage unit. So bit is often referred as 0 or 1. So when you have the 8 bits together, you make a byte, which is a character in computer terms. A byte is the smallest addressable unit. So that means you can independently access one byte from the memory. So consider the bit and a byte as the analogy of room and a house. So you have 8 bits in one byte, which are 8 compartments or 8 small storage units in one large area of one byte. Similarly, in one house you can have multiple compartments as rooms. So each memory cell has an address. So for every byte, you will have an address to access that memory location. So the address is again a unique number that identifies the location of byte into the memory. So there are two types of memories, the volatile memory and the non-volatile memory. The volatile memory loses its contents when power is turned off. Examples are the RAM, random access memory. On the other hand, non-volatile memory does not lose content when the power is removed. The examples include read-only memory, the flash memory, and the CMOS memory. So let's first discuss the usage and the working of the RAM. RAM is the acronym of the random access memory, and the data in the RAM usually has address associated with each byte. And then a CPU reads that data using that address, and as it is specified earlier that each byte has a unique address. So all semiconductor memory is the random access memory, and random access means individual words of the memory are directly accessed through wide in addressing logic. So in the RAM you have the feasibility to read the information and write the information back to the memory. It is again a volatile memory, it requires power to hold the data. A RAM must be provided with a constant power supply, so if the power is interrupted, the data are lost. So how much RAM should be necessary? It really depends on the need of the customer or the user. The amount of RAM necessary in a computer often depends on the type of the software that particular user wants to use. So for the starters, I think it is suggested that 2 GB or less is suitable for home and business users which use standard application software such as word processing or educational or other entertainment optical disc, or just using the social media, or 2 GB or less system, less RAM in a system will be quite useful. However, if you want to use the advanced multimedia capabilities, you should have a RAM 2 to 8 GB, or even in some cases if you involve high high usage of these programs, you should have 16 GB or even more than 16 GB of the um, RAM. And so if you are a power user, you should use 8 GB and more RAM for you. So this memory depicts a brief summary of different memory types, their categories, and their write mechanism, along with the volatility of their usage. So SRAM is a read and write memory, so you can read and write from this memory, and you can use the electrical level or the electricity to write and read from the RAM, and the read or write mechanism is based or addressed on the byte level. So it is volatile, so whenever you will turn off the power, it will lose all the content. The second type of memory is the read-only memory or the ROM, and it is read-only memory and programmable read-only memory. So you can not write in these type of memories, and you can also you cannot erase these memories. On the other hand, you can write a programmable ROM using electricity or electrical components whenever you want to rewrite your or whenever you want to write new instruction into the read-only memory. The Another variant of the ROM is erasable programmable read-only memory. So as the name suggests, it is the read-only memory, read mostly memory, but you can write as well because it is erasable. You can use the ultraviolet light to erase the memory, and it can be done on the chip level. So you can also use the electricity to erase the memory, and that variant is called EEPROM. Again, you can do it only byte level for this type of ROM. Another type of memory is the flash memory, which is electrically block level read only and read mostly memory, but you can also use the write operation as well. So all of the read-only memories and flash-only memory is non-volatile. That means it will hold the data even if you turn off the power. The next type of storage and memory is called registers. Registers are the special purpose memory units, and these are located inside the processor. So the processor contains small but high-speed storage locations which temporarily hold the data and the instructions. So these registers are the part of the processor, not the part of the memory or the permanent storage device. So there are different types of registers, each with a specific storage function, including storing of the location from where the instruction was fetched, storing an instruction while the control unit decodes it, storing the data while the ALU computes it, and storing the results of the calculation. So there are different kinds of registers available to handle different kinds of operations. So this is a small list. A CPU can contain many different kinds of registers for different kinds of operations. So almost all computers load data from a larger memory into the registers where it is used for arithmetic, manipulated or tested by some machine instruction. Manipulated data is then often stored back in main memory either by some instruction or a subsequent one. So registers also have different sizes. So number of bits the processor can have or the processor can handle specifies the size of the register. It is often termed as word size, which indicates the amount of data with which the computer can work at any given time. So it is the one block of the data that a computer can process at any single instruction. The larger the block indicates the more powerful your computer is. So you can increase by purchasing the new CPU. Use by so you can increase the speed of your CPU by increasing the size of the registers. So for example, in the old dated computers we had 16-bit registers and 32-bit registers. Current versions of the personal computers involve 64-bit registers. So as You can see in the diagram the CPU is divided into two parts, ALU and control unit, and it has another part of the storage which is the registers. So all of the information travels from the ALU and CU to registers and then from into the memory. Another type of memory is called the cache memory, and it is the small amount of very fast memory which stores copies of data from the most frequently used main memory locations. It sits between the normal main memory and the CPU. It may be located on the CPU chip or module. So it is used to reduce the average time to access memory. So as long as the most memory accesses are cached memory locations, the average access time of the memory accesses will be closer to the cache access time than to the access of the main memory. So another issue is the fundamental trade-off between the cache access time and the hit rate. For example, if you can have the larger cache time, the search time for specific information can also increase. Therefore, larger cache have the better hit rates but longer access time. So to address this kind of trade-off, many computers use multiple level of cache with small fast cache memory backed up by the larger slower cache memories. Multi-level cache generally operates by checking the smallest level 1 cache first, and if it hits, the processor proceed at the same speed. So if you are unable to find the information at the level 1 cache, the smaller cache misses. The next larger cache L2 is checked, and if that is also misses, the other levels can also be incorporated. So you usually have three level caches in current CPUs. Level 1 holds the recently used data, level 2 holds the upcoming data, and level 3 holds the possible upcoming data. So as the level increases, the size of the cache memory increases, but the access time to access the memory or any data decreases. So you can check the cache memory of your system through the task manager of your system. So this diagram depicts the CPU memory hierarchy. So the triangle depicts the fast access time from top to bottom. So whenever you are moving towards the top, the access time decreases. It will increase on the reverse direction. So if you look at the top of the triangle, you have CPU registers. So whenever CPU want to access some data from the register, it is accessed at a very fast pace. Then the cache memory is slower than the CPU registers. When you want to access some memory, some data which is not available in the cache memory, the data is looped into the RAM, and if the data is available, then it is moved to the CPU. So cache memory is faster than the RAM but slower than the CPU registers. So if the data is not available in the RAM, the data is fetched from the storage devices. So RAM is faster than the storage devices but slower than the cache memory. And even if the data is not available on the storage device, you request the data from the input sources. So the access from the input sources is slower than the storage devices. However, storage devices are faster than the input sources but slower than the RAM. So these are the trade-offs. First, if you want faster access time, you will have to spend greater cost per bit. So to increase the speed of your memory device, you have to ex you have to increase your expenditures per bit because CPU's registers are much expensive than the input sources or even from the RAM or cache memory. So you have to make the trade-off between these access time. Secondly, greater the capacity you have, smaller the cost per bit. For example, you have a 4 GB RAM and you can say the cost of the 4 GB RAM is about $50. Let's assume, and purchase the same you can purchase a storage device with the same amount, about maybe about 100 GB. So you can see the space in the storage device is greater than the space in the memory device. So when you have the greater capacity, you can see that the cost per bit is lower. Also, greater capacity induces slower access time because the system will have to go through a large portion to find out the specific information. So operations are performed by the processor. For example, as we discussed in the machine instruction cycle, fetching the instruction and decoding the instruction, performing some operation, and storing the result is also controlled by the CPU, and the CPU is controlled by a system clock. Typically, all operations begin with the pulse of the clock, and the speed of the processor is dictated by the pulse frequency produced by the clock, measured in cycles per second or hertz. Clock signals are generated by a quartz crystal which generates a constant signal wave while power is applied. This wave is converted into digital voltage pulse stream that is provided in a constant flow of the processor circuitry. So the system or the internal clock is the management of CPU instruction processing. So the rate of pulses is known as the clock rate or the clock speed at which your clock is changing or moving. So at any time your clock increments by one tick or the one pulse of the clock. That is referred as clock cycle, or the time it takes to turn a transistor off and then back on. The time between the pulses is the cycle time. It controls the timing of all computer operations, and a processor can execute an instruction in a given number of clock cycles. The machine clock cycle or the machine internal clock is the pace of the system clock, and it is called the clock speed. Modern machines use gigahertz processor or the 1 billion clock ticks in 1 second. So the system clock controlled processors are often called central processing unit, and it is characterized and distinguished by number of parameters such as its speed or clock cycle, number of and the size of cache memory, number of and the sizes of registers, word size, and speed of front side bus. So as you can see, the speed of the processor is measured in typically in hertz, and in current processors it is gigahertz. Size of the cache is in the kbs and in the MB. Number of registers, if your CPU has more registers and more higher the size of the registers, it will have more speed. Again, word size also had the proportional effect toward the use of uh, towards the increase of processor's ability to perform instructions. So there are different kinds of processors, and Intel is one of the most widely used processors in current environment. AMD processors are also second or third best options, and these are main competitors to the Intel, and these are originally produced by the company for budget friendly products. Another competitor for the processors is the IBM, and it historically manufactured mainframes. So this table shows a typical comparison of the CPU performance specification for three outdated systems. So it is just a comparison to show different kind of registers available in these processors. So as you can see, the different computers have the different register size. So the first two have the 16 registers, therefore the processing will not have much of the difference. However, the Power Mac G5 will have significant speed in terms of registers. On the other hand, word size is the amount of information or the data that a CPU can handle at any time, and in this case we can see the Intel lags behind the other two. Then there is the speed of the processor using the system bus speed, and again we can see the AMD processors are faster than the Intel processors. In the cache level, we can see these processors are first to introduce the cache memory, therefore these are faster than the Intel processors. So in terms of instruction execution, there are two types of CPU architectures or processor architectures. The first one is the CISC processors. CISC stands for Complex Instruction Set Computers. In the CISC, there is an option for single instruction to be decoded in multiple operations at low levels. For example, a single instruction can load the data from the memory, can perform some execution, and then store the data back to the memory. So it is capable for multi operations and accessing different kinds of modes within the single instruction. And these were used to directly support many high-level programming constructs such as calling functions, creating loops, and complex addressing modes. And it also helped to allow data structures and arrays accesses to be combined into a single instruction. So these architectures were made because software costs were more than the hardware costs. Therefore, writing code is more expensive than creating or purchasing hardware. So there is also need to incorporate the increasingly complex language at the high languages. Therefore, it leads to the large instruction set, more addressing modes, and ease of compiler writing, and improvement in the execution efficiency. Therefore, CISC complex instruction set computers were quite prevalent to counter these needs. So Intel 86 processors and Pentium series are the examples of these kinds of architectures. The second one is the reduced instruction set computing or RISC. Again, the name suggests it has the limited, smaller and simple instruction set, and it may process data faster because it can provide high performance if this simplicity enables much faster execution of each instruction. It is used across a wide range of platforms from cellular telephones and tablet computers. Large number of general-purpose registers or use of compiler technology is used to optimize register use. A RISC processor's emphasis is on the optimization of the instruction pipeline. They have the separate instruction for I/O and the data processing. So in the RISC, at most a single data memory cycle is exists as compared to the complex instruction set of the CISC CPU that may require dozens of data memory cycles in order to execute a single instruction. So the examples of RISC processors are ARM chips, MIPS, PowerPC and G5 Apple iPhone and iPad computers. Processors are also used in parallel to enhance the computation power, and multiple processors in a system with multi-core and multi-processor computers having multiple processing elements within a single machine lie in the domain of the parallel processing. Additionally, specialized parallel computer architectures are sometimes used alongside traditional processors for accelerating specific tasks. So this can be done using clusters or massively parallel processing systems and grids, which help to use multiple computers to work on the same task. In the massive parallel processing, thousands of processors in mainframe and supercomputers are used in a series. Parallel computer programs are also difficult to write than the sequential ones because you have to cater the issue of the concurrency. Concurrency introduces several new classes of potential software bugs, and of which the race conditions are quite common. However, this is not the top of discussion of our current course. Communication and synchronization between the subtasks is also some of the greatest obstacle to getting good parallel programming performance. So if you look at the current available environment, um, and you want to pick a suitable computer for your need depending upon the processing and memory uh, access requirements, you can make or purchase a computer system with respect to your tailor-made requirements. For example, if you want to use a computer for your home, an Intel Core i5 or i3 processor will suit you, and you should have a minimum of 2 GB RAM. For the office use, you can use the Intel Core i7 or i7 Extreme processors with minimum 4 GB of RAM, and for the mobile environment you can use an equivalent type of processor with about 2 GB of minimum RAM. So this concludes today's lecture, and if you want to read more about the topic, you can go through the recommended books or search the internet. And if you have any question, you can ask me through any of the designated medium, or you can conduct a question and answer session. Thank you very much.